I wish.
Okay, this is a courageous person, equally courageous as will be the next speaker. And we got 50 minutes to go. Come on.
Okay, thanks. Yeah, no, that's unfortunately not me. I wish it was me, but don't have time for that. Good. So I will talk in the next 1 hour about using spin-polarized STM to study quantum materials. Before I start, I would like to acknowledge all the people who contributed to the work, in particular my group in St. Andrews, and over the years, the number of people who worked on this has grown substantially. So right now, the team working on these kind of studies is mostly Divya, Carolina, Luke, and Christopher. And we studied samples from MPI Stuttgart, University of Augsburg, and University of Edinburgh. I don't show any of the data on the crystals from UBC Vancouver. I'll show some calculations from Sasha Yaresko and Christoph Heil from Oxford University. Obviously, I also would like to acknowledge funding, without which we couldn't keep our instruments code. If you wonder where St. Andrews is and where I'm from, so this is a map of Europe, with the UK still pretty close by. And we are located up here near Edinburgh. So this is zoom in here. St. Andrews sits here on this peninsula here. And it's actually a pretty nice place. So this is a photo of the beach, which is something like 500 meters away from the physics department, and between the physics department and the beach is the golf course. And this is the medieval town of St. Andrews. If this got you excited, we currently have a postdoctoral position open, so please go and check it out if you're interested, and if you find the kind of work I'm presenting interesting. Okay, so before I start to discuss our own work, let me briefly give a motivation why we want to use spin-polarized STM to study quantum materials, and why we want to study quantum materials in general. And you've seen this kind of chart already a couple of times. So in 1986, the high temperature superconductors were discovered, which gave hope that we might have this kind of technology. And we know that right now we are starting to see the first electrical vehicles on the roads, but nothing which is running on superconductors. So it's more than 30 years late to come to that development. That's not to say that we don't have any technology yet based on superconductors. So I guess in particular, people from Spain will know about this video here, where a Japanese car company wanted to show off their technology leadership by building some truly innovative technology. So this plays in, this was done in 2015, this video. Slight irony is that they asked the German engineering company to build the thing. And so you see, this is coming pretty close to the kind of gadget working on superconductors we would like to have. But you can also see that it has a couple of serious drawbacks. One of them is that you still have to cool it with liquid nitrogen, obviously. But the other one is that they always fall off after a couple of meters. And you can think for yourself why they fall off. It's because they have to have a rail underneath, which kind of keeps the thing levitating, so they can only go on that rail. And so basically they can't balance the thing. But there are more serious applications of superconductors. So for example, in Japan, they built this superconducting maglev train. Now, very frustratingly for us who are working on quantum materials, this train here is built on conventional superconductors. So actually, it's not, if you like, a success of materials research, but it's a success of cryogenic cooling technology, because they can now build cryocoolers so well that they can actually put in a train which runs around at 600 kilometers per hour. But that's not what we are working on. Before I start to talk about our own research, I think it's worth pointing out that, well, one of the things we would like to do is understand why high temperature superconductors become superconducting, so that we can get them to a higher transition temperature. But it's also worth keeping in mind that these materials have a whole load of other interesting and potentially technologically important properties, such as, for example, a high thermoelectric coefficient, or you could, for example, think about using the Mott effect for memory devices or for transistors. And just as one example, in sodium cobaltate, already in the 90s, people discovered that it has a very high thermoelectric figure of merit, and what you can use that for example, already in the 1960s in Russia, people had this idea of a thermoelectric lamp which would power a radio, which you could use in places where you don't have a grid, an electric grid. And to more serious applications nowadays, car companies, for example, are considering putting thermoelectric converters in cars to basically use the exhaust heat and thereby increase the efficiency of these cars. Okay, by now coming to why and how we can use spin-priced STM to learn something about the properties of quantum materials. You have seen these sort of phase diagrams already a couple of times. And what's common to them, which has also been discussed already a couple of times, is that you have a magnetically ordered phase which is close to a superconducting phase, and quite often where the magnetic order is suppressed, you get superconductivity. Whether or not there is a quantum critical point is controversial, as you've heard, but in both these cases, so here in the phase diagram for the cuprates, you have an antiferromagnetic mod insulator at zero doping, the mysterious pseudogap phase in between, and then superconductivity emergent. In the iron-based superconductors, a magnetostructural phase transition is suppressed, and the suppression appears to happen right where you have the optimal doping for superconductivity. So this tells you that that somehow superconductivity and magnetism in these materials are intimately related. And one way in which we can try to study on a microscopic scale the phase relationship between them is to use spin-priced STM to image how the magnetic structure looks like when actually this phase enters into the superconducting regime. Okay, in my talk I will first discuss how we do spin-priced STM, and if you like, basically show you a calibration of the method, that we can actually measure magnetic order in quantum materials, and then show you some more recent results where we've actually tried to go into the superconducting phase to see what the relationship between magnetism and superconductivity in one example is. Okay, so my group operates a suite of scanning tunneling microscopes. So if you like, we are explorers, and explorers need ships, and the STMs are our ships. So this here is an image of the Discovery. This was the ship which Scott took to go to the South Pole. And the ship happens to be near St. Andrews, so if you come to the region, you can have a look at it. It's a very nice museum. This is the party of Scott who went to the South Pole. And you can see that if you look at them, this is shortly after they arrived there. They all look a bit disappointed. So it turns out they were second at the South Pole. So they arrived there and they saw the Norwegian flag. So that's why they look so disappointed. So obviously we want to use our ships to boldly go where no one has gone before. It doesn't always work out. Sometimes we'll be second. So this is, if you like, our ship here. This is the ultra low vibration labs in St. Andrews, where we have our scanning tunneling microscopes. So that they all sit on concrete blocks which are isolated from the floor and which sit inside acoustic enclosures to basically minimize any impact of vibrations or of acoustic noise. And the instruments we operate are all home-built. They sit in commercial magnetures, and then the microscope heads are made out of sapphire because it has a very high stiffness and a high thermal conductivity. And we currently operate 3 of them, 2 of them at 1.6 Kelvin, and one sits in a dilution refrigerator. If you wonder why do we need such a complicated building to do scanning tunneling microscopy, well, you can think by scaling it up. If you think about the tallest building in the world, that's Burj Khalifa, I think, still, which is 828 meter high. If you scale that from the size of the STM tip, you would have to bring the sample within 50 micrometers of the tip of that tower, and without it touching, right? That kind of sets the scale. So in our case, the tip sample distance is on the order of 3 atomic radii, something like 5 angstrom. And if you consider that your tip is on the order of 10 millimeter large, that kind of gives you the scale, given here of 50 micrometer. And basically, whenever that tip is shaking a little bit, it creates noise in the measurement and basically renders the measurement more fuzzy than you would like it to be. Now, to briefly introduce STM, because I think this is the first, if you like, pure STM talk, what we mostly use, or what I will mostly show, is constant current imaging. So we maintain the tunneling current constant by a feedback loop. I apologize for the slightly messy slide. So we measure the current between the tip and the sample after we apply voltage. and then feed that to a feedback loop and try to maintain it constant. And if we then move the tip across the surface, we can record how we have to regulate the tip sample distance z, and that gives us a topographic image. Okay. So if I scan this tip here across some feature on the surface, then basically my current stays more or less constant, apart from small variations which are needed to regulate the feedback loop. And I can record the Z signal which traces out the trace of the surface. And this will be relevant for what I'll explain in the following. Well, in addition...
If your sample has lots of current noise, is this something that would spoil the experiment, or is something you can exploit?
So, well, it is something one can exploit. I wouldn't claim that we can exploit it. So we currently use a current amplifier which has a low bandwidth on the order of a kilohertz. Okay. So most of the kind of fluctuations you would have in the sample happen on much faster timescales, so we wouldn't see them. But there are people working on actually trying to look at fluctuations by, for example, putting high frequency amplifiers into the STM. So it's possible, but it's not easy, because typically we work at very low currents here, and in order to measure these very low currents, you have a relatively small bandwidth of your amplifier. Okay. In addition to the topographic information, we are interested in spectroscopic information, and if you like, the equation for relating the tunneling current to spectroscopic information in the sample, so to the local density of states. This has been derived already by John Bardeen when people studied planar tunneling junctions with superconductors. So it's this equation here which contains a convolution of the sample density of states and the tip sample density of states. And when looking at this equation, there are a few things which are worth keeping in mind. One of them is that the whole measurement is symmetric in tip and sample, so you will always measure both the tip density of states and the sample density of states. And the other one is you have Fermi functions here, which basically means that the temperature of your measurement limits the spectroscopic resolution which you can achieve, which is one of the reasons why we would like to do these measurements at low temperature. And one can simplify this equation by assuming that one is in the zero temperature limit, and then it basically just becomes a convolution of the tip and sample density of states. And in a measurement, if you apply a bias voltage, basically your electrons tunnel from the tip to the sample or from the sample to the tip. And if you measure the differential conductance, it basically retraces the density of states of the sample. And that's, if you like, the spectroscopic power of scanning tunneling microscopy, at least as long as you have a normal metal tip. Okay, and so this is basically just restating an equation, what I just said. And just to, on the resolution, so the resolution of the STM is basically determined by the measurement temperature. So one can show that the instrumental broadening is 3.5 times kBT. So if you're at a temperature of, for example, 10 millikelvin, which is, I think, the lowest temperatures achieved in scanning tunneling microscopes so far, then you would get an energy resolution which in the minimum would be on the order of just a few microelectron volts. Okay, and what we can do with this technique is we can now, from one measurement, get topographic information as well as spectroscopic information, and the spectroscopic information we can obtain by taking such a tunneling spectrum at each point in such a topographic image, which gives us such a three-dimensional data set of the density of states at each point in a finite area. And then we can use this, for example, to study things like a local gap size, influence of defects, inelastic excitations, and local ordering. And then what's typically done is that one also looks at the Fourier transform, which can give information about quasi-particles, charge density waves, lattice distortions, or, as I will show in the following, also about magnetic order. And this has been highly successful in studying, in particular, the cuprates. So Seamus Davies has done a lot of work to study the quasi-particle interference in cuprates and detect this kind of local charge order, which has been seen in underdoped cuprates. And one of the obvious questions is, well, if you see this kind of charge order, there's been a lot of speculation whether this kind of charge order is actually accompanied by magnetic order. Because there have been predictions that in these materials you would get basically a periodicity of 4 unit cells of a spin charge separated order, And I think that's still one of the outstanding questions, whether actually there is magnetic order underneath these kind of structures. And that's one of the reasons why it's actually of interest to use spin-polarized STM to study these kind of materials. In order to do spin-polarized STM, we need to use a magnetic tip, and then this equation for the tunneling current gets modified, and now we have the product of the spin-up density of states of sample and tip and the spin-down density of states of the sample and tip. This is a simplified version of the equation. In reality, you also have a direction cosine between these terms. So this is assuming that the magnetization of the two are parallel. If they are at an angle, then you would, in addition, get a direction cosine here. And what this means is, if now the spin polarization of the tip and the sample are parallel, then basically you get a large tunneling current, as shown by this large arrow here. If, on the other hand, the magnetizations are anti-parallel, then your tunneling current becomes suppressed. And if you take a topographic image, because the STM tries to keep the current constant, what it means is that your tip will actually move slightly closer to the surface, so those areas will appear slightly lower in the constant current image. And this was basically the basis for the first demonstration of spin-polarized STM by Roland Wiesendanger already in the 90s. So he used an antiferromagnetic tip and studied a chromium 001 surface where you have basically ferromagnetic layers but alternating with opposite spin direction between adjacent layers. So if you look at adjacent terraces, they have opposite spin, but within the terrace, the spins are in the same orientation. And now if you use a magnetic tip to scan across step edges, then you detect different step heights dependent on whether you move from a terrace where the spins are parallel to one where they are anti-parallel, or the other way around. And this is showing his measurement here. So this is two step edges with a non-polarized tip, and you can see a step height of 0.14 nanometers. And then he has imaged two step edges with a magnetic tip, and then you can see how the step height alternates between 0.16 nanometers and 0.12 nanometers, and then it goes back to 0.16 nanometers. And basically this was the first, if you like, demonstration that you can use an STM to image magnetic structure. I think at the time, so this was before I entered actively in science, so I can't tell that from my own experience, but I understand that at the time the result was somewhat controversial because people thought that just from these line cuts it's a bit difficult to tell whether this is really a magnetic tip or maybe, for example, a double tip. People who do STM know that quite often you can see strange step heights just because you have a double tip, for example. So if you like, what was missing is, so here in this case they had to take the tip out and approach with a different tip to do the magnetic measurement. What one would like ideally is that you can actually change the magnetic properties of your tip while you scan on a particular area on the sample. So if you like, what gives you the magnetic contrast is that basically due to the change in the tunneling current, you get a change in the tip sample distance because the tunneling current will be maintained constant, and the change in the height you get is proportional to the spin polarization of your tunneling current. And if you now want to prove that what you get is magnetic contrast, in an ideal world what you do is you scan the same area with a tip which is magnetized in one direction, and then with a tip which is magnetized in the opposite direction, and then you should see immediately a change in contrast which would give you the opposite contrast basically in the same location.
So, can I ask a
yes.
question? You said the tip was antiferromagnetic.
In this case, the tip was antiferromagnetic,
So
that's
the
right.
magnetization of the tip that you're referring to is somehow just the moment on the last atom of the tip?
Yes, that's the interpretation, yeah. Now, we don't use antiferromagnetic tips, but they are quite commonly used. And so, one point is obviously in the end, your contrast depends on the last atom, if you like, on the last cluster. How do you define antiferromagnetism of a small cluster of just a few atoms, right? Or of the last atom, if you like. And in addition, there is an advantage of using antiferromagnetic tips because you minimize stray fields. If you use a ferromagnetic tip, then you get larger stray fields from the tip, which might interact with the sample, depending on what you're looking at. Okay, there is in principle another way in which you can demonstrate whether what you see is magnetic contrast or not, and that's in fact from spectroscopy. So here's an example of a DIDV spectrum of basically a Stoner split state, where you have an exchange split state, where you have the spin up state below the Fermi surface and the spin down state above, and then if you reverse the polarization of the tip, you basically see a change in intensity. And so that's in principle an alternative way in which you can prove that what you see is magnetic contrast. Okay, so how do we get a magnetic tip? And one possibility which I'll not show any of which we are not using, but I'll show for completeness. In principle, you can use a superconducting tip and apply a magnetic field to spin split your BCS gap. So this is a technique which has been used extensively in planar tunneling junctions by Tedro and Messabe. So there's a whole review article about this. So the principle is you apply a magnetic field. If your tip cluster, if you like, is, or in these planar films, if your field is in the plane, you don't get orbital screening currents, and basically then you can split the BCS density of states, and if the spin-orbit coupling in the superconductor is sufficiently small, and then you can use these spin-polarized coherence peaks to probe the spin polarization of the sample. So if you tunnel to the Fermi energy of the sample, then basically the change in intensity with which you see these coherence peaks tells you directly, quantitatively, what the spin polarization of your sample density of states at the Fermi energy is. So in principle, this is very elegant, but it's also very difficult. So to my knowledge, this has only been achieved once by Christian Ass and Klaus Kahn in Stuttgart. So here they use a vanadium tip, and then they apply a magnetic field. This is the superconducting gap in their spectrum. And then as they apply the field, you can see the splitting of the coherence peaks. And then, so this is a calculation which shows it a bit clearer. And then if they go onto a magnetic island with that tip, this is a cobalt island on a copper 111 surface, then you can see this asymmetry in the tunneling spectrum. It is an extremely difficult measurement because it has to be done at low temperature, at very low temperatures, so this will be below 100 millikelvin, so that you can actually properly resolve the spectrum, and you have to apply a field on the order of a few Tesla in order to actually split your density of states. So if, for example, you study something which reacts to the magnetic field, then this may well not be the method of choice. But on the other hand, it gives you quantitative information about the spin polarization of your sample. Okay, the other method, which is the one which was pioneered by Roland Wiesendanger, is that you make magnetic tips. And so what they do is they use a tungsten tip and then remove first an oxide layer and evaporate magnetic material on the tip. And then dependent on how much material they evaporate and which material they can control what the magnetization direction at the tip is. It's worth noting too that this is a fairly complicated procedure because they have to heat up the tip to 2200 Kelvin to remove the oxide, then evaporate material on it, and then bring it into the STM. So this is not the method we chose. And then there's also an alternative, is you can just use a tungsten tip and try to pick up some magnetic material from your sample, for example, or from a calibration sample, and thereby render your tip magnetic. And that's basically the approach which I will show in the following. Okay, before I come to what we see with STM, let me mention just two limitations of spin-polarized STM. One of them is, well, it's very fashionable these days to study topological insulators and rush-pass spin-split states. So spin-polarized STM unfortunately does not allow you to resolve different spin-polarized branches of your Fermi surface, because what you see is always only the average of these branches. So you only see the non-polarized part, whereas with photo emission you can resolve these. The other thing we don't see, because we probe spin polarization at the Fermi energy, you don't detect, for example, things like loop currents, which are proposed to exist in the pseudogap phase of the cuprates. Okay, in the following, I will discuss measurements on iron tellurium, so if you like, the non-superconducting parent compound of the iron chalcogenide superconductors. And one of the reasons why we chose to study iron tellurium is because if you cleave the material, it's a non-polar surface, and you don't cleave into any of the dopant layers as you would do in the 1,2,2 compounds or the 1,1,1,1 compounds. So you can assume that your surface is reasonably representative of the bulk material. Okay, this is the phase diagram of the iron chalcogenides. So iron tellurium sits here at the left hand, and as you dope the material with selenium, you drive the material first into a spin class phase, and then it becomes superconducting. In the undoped compound, you have this bicollinear magnetic order. This was detected already in the 1970s by neutron scattering. So this is shown here. So the material is known for a quite long time. And what they deduced at the time is the correct ordering wave vector. But they deduced that these spins here point out of the plane, whereas modern neutron scattering studies tell us that these spins here lie actually in the crystallographic plane, in the AB plane of the material. Okay, one detail which I haven't mentioned so far is one can't actually make stoichiometric iron tellurium crystals, but they typically have some excess iron in them. And as a function of this excess iron concentration, they have a relatively complex phase diagram where you start out for low excess iron doping with this bicollinear magnetic order I've just shown you. But then as you increase the excess iron doping, the material goes through an incommensurate spin density wave phase and then ends up in an orthorhombic incommensurate helimagnetic phase, according to neutron scattering. And there have been a couple of theoretical proposals as to why the material undergoes this transition here. So for example, one proposal is that basically this is due to doping from the excess iron atoms. It has been proposed that in the low excess iron regime, the magnetic order is dominated by quantum fluctuations, and also that the structural distortion is what might drive this bicollinear order. And I'll try to address whether we can, based from our measurements, exclude or confirm some of these proposals. Okay, if you cleave the material, the cleavage plane is between these iron tellurium layers, and one basically should at the surface see a square lattice of these tellurium atoms, which are these dark atoms here, whereas the iron lattice is 45-degree rotated, a 45-degree rotated square lattice underneath. So what we expect to see then is that this is, if you like, a sketch of the structure in the top view. We should see these dark atoms here on a square lattice, and if we take the Fourier transform, we see these atomic peaks here predominantly, and then the iron lattice would be at these larger wave vectors here. Now, if we have a magnetic tip, then we should basically see the magnetic order, this bicollinear order here, and then in the Fourier transform of such an image, we should see additional peaks halfway to the tellurium peaks in the direction of the a-axis of this material. Okay, this is an STM image taken with a non-magnetic tip on a freshly cleaved iron tellurium sample. You see a couple of excess iron atoms here sitting on top of the material. As I mentioned, it's not possible to grow the material exactly stoichiometric. And this is a Fourier transform, which sure enough only shows those four Fourier peaks due to the atomic order. And now we can basically use our STM to pick up some of these iron atoms here and thereby render the tip magnetic. Okay. So here you see an STM image where some of these iron atoms are still on the surface, but some of the iron atoms are gone from the surface and they are now attached to the tip, which renders the apex of the tip now spin polarized, and hence we now suddenly see this double stripe order running vertically through the image, and if we take the Fourier transform, we see these additional peaks due to the magnetic order in the material. Now, I mentioned to you, well, okay, now first of all, we can see this also in larger areas. If we scan basically, this is for example 60 by 60 nanometers, you can see these stripes running basically everywhere through the sample, always in the same direction, and only when we have twin boundaries, for example, they change direction, and we can also analyze the angle of these twin boundaries, and it's consistent with the bulk properties of the material. Now, I mentioned to you, in order to prove that what we see is actually magnetic contrast, we should change the magnetization of the tip and see how our magnetic contrast changes. So these are two images here taken in the opposing magnetic field, in a magnetic field which is normal to the surface. And the white line here is a guide to the eye. You can see from the defects that these two images are taken in the same location. But what you can also see is that these vertical stripes have changed phase between the top and bottom image. So here these three defects are, if you like, right on top of one of the dark rows, whereas here they sit on top of the row. So the whole pattern has basically shifted by 180-degree phase shift between the top and the bottom image. And now we can use that information to extract what the unpolarized image would look like, as well as from the difference. So this is by taking the average of the two images, and from taking the difference, we can get an image of purely the magnetic contrast of the surface. And so this is now a priori just a height difference, but we can actually calibrate that. So one can show that the spin polarization is essentially proportional to that height constant, and we can measure this proportionality constant by measuring a curve as how the current changes as a function of tip sample distance. And if we do that, we can convert this to a proper spin polarization scale, and basically what it tells us is that the spin polarization across the sample here is up to 10% of the tunneling current in this specific case. Okay, in addition, what you can also see is that the maxima of the magnetic order is actually occurring between the tellurium rows, which is what you would expect because the magnetic order comes predominantly from the iron atoms and not from the tellurium atoms. Okay, so basically this confirms, if you like, this magnetic structure which has been seen in neutron scattering before. Now, we're not the first ones actually to see this, I should mention. So this kind of stripe order has been seen a couple of times before. But basically, if you like, the missing piece of the puzzle was to understand that the fact that one sees the stripe order simply meant that the tip had become magnetic in the course of the measurement, because one basically picks up these iron atoms almost accidentally already, even if it's not on purpose. So basically by preparing the sharp tip. So effectively all these studies have been spin-polarized STM studies without noticing. Okay, one of the questions we were wondering is why do we see magnetic contrast in the material, given that the top layer is tellurium, which is a non-magnetic element. And so we've asked Sasha Yaresko to do DFT slab calculations of the surface. And what one basically finds is that at the surface, well, the iron surely is spin polarized, that's to be expected. But actually also on the tellurium atoms at the surface, at the Fermi energy, you have a substantial difference between spin up and spin down density of states. So also the tellurium states are reasonably strongly spin polarized. Okay, one of the predictions which has been made both for the cuprates as well as for the iron-based superconductors is that if you have a spin density wave modulation, you should have an accompanying charge density wave modulation which has twice the wave factor of the spin density wave. And if you like, that's basically saying that the electronic structure in the middle of one of these domains is different than at the boundary between two of these domains. And so let's see whether we observe that. So this is a unit cell averaged topographic non-polarized image, and this is the corresponding spin-polarized image. So in the spin-polarized image, you see the magnetic structure as expected, but you can also see in the non-polarized image that in fact you see stripes running vertically through the image, and if I compare a line cut in the horizontal and the vertical direction, I can see that the corrugation in the horizontal direction is twice as much as it is in the vertical direction, also in the non-polarized image. So we do see a charge modulation also, well, a modulation also just in the charge channel induced by the magnetic order in the material. Now you could say, okay, maybe this is just a tip artifact and the tip is slightly asymmetric, but in fact, if we scan this across two different domains with the same tip, you can actually see how these bright points here, which are the atomic Bragg peaks, change direction with the same tip, which confirms that this is really the charge order associated with the magnetic order and not just a tip artifact. Okay, and we can also compare this to DFT calculations. So these are plane wave DFT calculations which enable to simulate STM images. So this is a topographic STM image calculated from paramagnetic calculation, where basically you have C4 symmetry around the atoms. And then if you calculate the non-magnetic image from a magnetic calculation, so just the topographic image from the magnetic calculation, you see in fact the same asymmetry as we see in the experiment reproduced. And okay, the magnetic spin-polarized image simulated from these calculations looks not surprisingly exactly the same as in the measurement. Okay, now one of the puzzles when we took this data first was that the magnetic order according to neutron scattering, as I mentioned previously, is purely in plane, whereas the magnetic field we apply is normal to the surface. So if we polarize our tip normal to the surface, in principle we shouldn't see any magnetic contrast. So we shouldn't see any of this. Okay, so one of the questions was, why do we see this magnetic contrast at all? So to study, if you like, the direction dependence of our magnetic contrast, we first need to establish what the magnetic nature of our tip is. And we can actually control that by how we prepare it. So one possibility is we can make antiferromagnetic tips if we really pick up a large cluster of the material. And then if we change the magnetic field, there's no change because the tip doesn't follow. Or we can make ferromagnetic tips, like the one of which I've just shown the data, where basically as a function of field we can essentially record a hysteresis loop of the tip if we subsequently record topographic images of our sample surface. And so basically by controlling how much excess iron we pick up or whether we pick up a flake of the material, we can control whether the tip is ferromagnetic or antiferromagnetic. And if we have a ferromagnetic tip, then we can use a vector magnetic field to basically orient it in any given direction to map out what the spin direction in the material really is. And okay, and so to that end, we built an STM which sits in a vector magnet. So this is an image of the STM. You can't really see much. So this is a vibration table. The magnet viewer hangs down here. And the STM has a 9 Tesla vertical field and 5 Tesla horizontal. But that only gives us 2 axes. And so the third axis we achieve by having the insert rotatable. And that basically means that we can have 5 Tesla in any direction with respect to the tip sample geometry. And this here is an image of the turntable device with which we rotate the STM. And surprisingly, this works pretty well without changing the tip. And while I try to discourage my PhD student from doing that, he can even rotate it when the field is switched on without changing the tip. Okay, so this is the data for low excess iron concentration. This is now a measurement where we use exactly the same tip and image exactly the same location on the surface, but now once in a magnetic field which is in what we call oriented in the x direction. So what we do is we take an image where it's in the plus x direction and subtract an image where it's in the exact opposite direction, the minus x direction. Then we do the same thing, applying the field in the plus y and minus y direction and get the difference image, and then the plus z and minus z direction and take the difference image. All with the same tip. And from that we get these 3 spin-polarized images of the magnetic contrast of the surface, and then we can basically use them to reconstruct what the magnetic order in the material looks like. And this is now here a rendering where each of these yellow points represents one of the iron atoms, and these little arrows here indicate the direction in which the magnetization in the sample points, and then they are colored in blue or red depending on whether they point into the image plane or out of the image plane. And what you can see is that while one can recognize sort of the double stripe order, they are actually not in the plane. They have an angle out of the plane. And we can analyze that angle as a function of position, and what we get is that the angle is basically plus or minus 30 degrees. And it's not only us who have seen that, but also the group of Professor Wiesenberg in Hamburg. They've done the same measurement, and they get the same angle, which is somewhat reassuring because it means that the method is reproducible between different labs and gives the same result. So this is still sort of a puzzle why we see a different angle as is seen in neutron scattering. So we are now working with Chris Stock, who's a neutron scattering expert, to see whether this means that potentially there are other possible interpretations of the neutron scattering data, or whether this means that at the surface the magnetic structure is reconstructed and basically relaxed outwards from the surface. Somewhat surprisingly, so after we got this result, we asked DFT people to do fully relativistic calculations, because then in principle they can get the lowest, well, the angle of the lowest energy of the spin configuration, and they get the same angle as we get for the bulk. So now the question is whether, well, either the DFT is inconsistent with neutron scattering, or there's some issue with, yeah, either there's some issue with the DFT or with the neutron scattering. So that we'll need to still figure out. Okay, let's go to higher excess iron concentrations. I mentioned to you that higher excess iron concentrations, the magnetic order gets more complex. So at 12% excess iron concentration, according to neutron scattering, we should get into a helimagnetic incommensurate phase. So these are again images at plus and minus 4 Tesla, now along the direction of these stripes here. And what we see in the difference image is the magnetic order. And what we also see is that now the maximum of the Fourier transform is not anymore at a commensurate wave vector, but actually has moved to an incommensurate wave vector. So we see at high excess iron concentration, consistent with neutron scattering, that the magnetic order becomes incommensurate. And what we also see is we can also rotate now the magnetization of our tip by using the vector field, and we can trace how these stripes change. And in fact, we see these stripes, so these are 3 images taken at different magnetic field angles, and what you can see is that these vertical stripes here move underneath these vertical white lines. It's maybe not so easy to see in these images, but here's a series of line cuts taken in the same location, and you can see that these maxima here move as a function of field angle. So we can clearly show that the magnetic order shown here is in fact a spin spiral, and as we project on different spin polarizations of the tip, the phase of the stripe order moves across the sample, which is what you would expect if your image is spin spiral. And this here is basically plotting the maximum of the contrast here, the position of the maximum as a function of field angle. So basically on samples with high excess iron concentration, where all the excess iron is still at the surface, we get consistent results with the neutron scattering measurements. Now, I mentioned to you that we can also remove the excess iron, and so we can actually look at what is the effect of removing some of the excess iron from the surface on the magnetic order. So here's an STM image where on the right-hand side we still have the excess iron at the surface, and on the left-hand side we have removed the excess iron from the surface. So now you have a surface layer which has half the excess iron concentration from the bulk underneath. And what you can see in the Fourier transform is that whereas at high excess iron concentration at the surface, we get this incommensurate order here. Once we've removed this excess iron at the surface, now the order becomes commensurate. That's actually easier to see in this line cut here. So the green line is from the line cut from the right panel, and the blue line from the left panel. And you can see how where we have removed the excess iron, suddenly the magnetic order becomes commensurate. So basically what we see from that is that as we change the excess iron concentration at the surface, the magnetic order changes as well. So we can basically study configurations, if you like, where the surface layer has a different excess iron concentration from the bulk material. And now we can also do this at even higher excess iron concentrations. So this is now for 20% in the bulk, and the surface has 10% excess iron concentration. And this is the non-polarized image. This is now again the polarized image. And what we now see in the Fourier transform is that now all of a sudden we start to get magnetic order in both directions. So we get basically a double Q order of the magnetic structure. And interestingly, the intensity of these wave vectors changes as a function of field angle, and so which points out that this is a fairly complex magnetic structure. So to map out what the exact magnetic structure is, we've recorded the intensity of these peaks as a function of field angle, and what we then get is for the in-plane angle, we can see that basically both these maxima disappear at the same angle, which tells us that the magnetic order for those 2 points, the spin direction points in the same direction. But for the out-of-phase plane angle, actually they behave quite differently. So one of them behaves like a spin spiral, whereas the other one is suddenly suppressed once the magnetic field goes to an out-of-plane angle. And so then the PhD student who did this study, he was able to actually make a model of what the magnetic structure is, which corresponds to that. So he came up with a model where one has a spin spiral which runs along, well, 2 spin spirals which run along the iron-iron directions. And with that model, he can fully reproduce basically how the magnetic intensity changes as a function of angle. Okay, if we now compare all our measurements with Neutron scattering, we can draw a phase diagram from what we can derive from the surface magnetic order in comparison to what's known from Neutron scattering. So what's plotted here is the intensity of the magnetic order in the 2 directions, basically of these 2 wave vectors, as a function of excess iron concentration, and the blue points here are the incommensurability from Neutron scattering. And what's interesting to note is in the monoclinic phase, at low excess iron concentration, we see only magnetic order in one direction, and this is where Neutron scattering sees commensurate order in one direction. So that's completely consistent. And then as we come to high excess iron concentration and the material undergoes a phase transition to orthorhombic structure, the Neutron scattering shows this incommensurability, and we start to see this double Q ordering in the orthorhombic phase, which is where basically the 2 lattice constants become more similar to each other, and you start to get this formation of a blackhead magnetic order, which is well shown by the fact that you see intensity in both directions. Okay, and if we compare this now to the theoretical models which have been proposed for the magnetic order, I think from our data we can basically exclude that it's just a doping effect, if you like. Because if it was just a doping effect from the excess iron atoms, then by removing excess iron from the surface, we should always be able to go back to the bicollinear magnetic order, which is, however, not what we see. Right? If we remove the excess iron here, even in the high excess iron doped samples, we still see a blackhead order with magnetic ordering in both directions. So this would either support the quantum fluctuation picture, or in a way both, or that actually the structural distortion of the material is responsible for the formation of the bicollinear order at low excess iron concentration. Okay, I showed you so far what happens if we go along, if you like, the third axis of this phase diagram to high excess iron concentrations. Now I want to briefly show you what happens as we dope selenium into the material and drive it superconducting. So here are 3 STM images taken at these 3 doping levels. So this is the pure excess iron, pure iron tellurium, which I've shown you so far. This is a 10% selenium concentration, and this is a 15% selenium concentration right here at the boundary. At 15%, we basically see that we don't see any magnetic order anymore. We just see the atomic structure, and we see a superconducting gap. At 10% selenium concentration, you see that there are patches where there is magnetic order, next to patches where there's no magnetic order, and this is basically close to what's called the spin class phase in this phase diagram, where I should mention that these phase diagrams in the details here, they depend on which publication one exactly looks at. So if we look at a larger scale image in this 10% excess iron dope, 10% selenium dope sample, So you first of all see that the magnetic order becomes patchy. This is again a spin-polarized image. But you in addition see that you have now stripes running in both directions. So you see it's predominantly in this direction here, but occasionally you also see stripes running in the perpendicular direction. That's the 10-minute sign. So basically we see this broad peak here, which corresponds to the dominant order, but there is a secondary peak which is not very well visible in this image here, which basically comes from patches where the magnetic order is in the normal direction. Now, first we can again check, is this really magnetic order? So we apply a magnetic field, plus and minus 5 Tesla. It's very difficult to see by eye in these images, but if I take the difference, one sees kind of patches where the order runs in this direction here, and then there are also patches where you see it running in the orthogonal direction. And if you like, effectively what this is imaging the spin class phase in the iron chalcogenides. Now, one question is it just that we see only in specific places an increased spin polarization of the magnetic order, or is the magnetic, so in this case it would be coherent through the sample, or do we see different clusters where the magnetic order is completely independent, in which case the phase should not be coherent throughout the sample. So we can basically analyze the phase, so this is the amplitude, we can analyze the phase of these stripes, and if you look at a plot of the phase, you can see that this patch, for example, here has this yellow phase, but then, for example, this patch up here has this blue phase, which is shifted by basically a quarter, well, it's by pi over 2, which tells you that the phase is actually independent between the different regions on the surface. So these are really small clusters of magnetic order, which are independent from each other. And the kind of the coherence length of this magnetic order is on the order of a few tens of nanometers, and that's consistent with what is seen in neutron scattering at this selenium concentration. Okay, now the interesting question is obviously what kind of relation do we see to superconductivity? So first to show you that the sample actually is superconducting. It's not a great superconductor, but it is superconducting. So this is a resistivity curve measured on the same sample, which drops here at around 8 Kelvin. This is an average tunneling spectrum. So you see this albeit broad, but you see this gap around the Fermi energy. And now what we've tried to do is basically correlate whether we can see any systematic variation of that gap with whether or not there is a high intensity of the magnetic order. So to do that, we've taken the topographic image, which came with a map, and analyzed it for the intensity of the magnetic order. So this is a map of how strong we detect the magnetic order. And then we've tried to correlate this with how strong we detect the superconducting gap. You can do that in different ways. For example, you can compare the zero bias conductance with the intensity of the magnetic order. You can see that some features are actually kind of consistent. So here we have a high zero bias conductance and a high intensity of the magnetic order. But in other regions, there's no correlation. So for example, for this bright spot here, it's a dark spot here. So there's no clear correlation between the two. So because it's only 10 minutes, let me jump over the slide. So if we now plot, if you like, the tunneling spectra averaged over regions of the same intensity, this is what you obtain here. So this is for basically lowest intensity of the magnetic order, the tunneling spectrum. This is for highest intensity, and you see hardly any systematic you don't see any systematic variation. So basically the gap looks exactly the same whether we have strong magnetic order or weak magnetic order, and we have confirmed that over different data sets, and it always looks consistent. And to show you that this is the superconducting gap here, I compare spectra taken on samples with different selenium concentration. So we see basically the same gap size at 0.4 and 0.15, at 40 or 15% selenium concentration, and this here is at 10%. So the gap size is the same in each case, except in iron tellurium, where we don't have the superconducting gap. And it's worth pointing out this is also consistent with what's seen in thin films. So this is a measurement from the group of Professor Wiesendanger again of an iron tellurium film on bismuth telluride, where they see the magnetic order and at the same time a gap which looks like a superconducting gap, which is perfectly happy to coexist with the magnetic order. So if you now look at how that's consistent with theory, well, there's a whole bunch of theories describing how the magnetic order should be related to superconductivity in the iron-based superconductor, and I will concentrate on basically on this paper here, but essentially they are consistent in saying that if you have an S++ order parameter, that should be suppressed by magnetic order, but if you have an S+- order parameter, that's actually reasonably happy to coexist with magnetic order. So this is a phase diagram from the paper from our chair of the session, which basically shows that for the S+- state, the superconducting state happily coexists with antiferromagnetic order, whereas for the S++ state, it would get very quickly suppressed. Okay, and since my time is up, I'll summarize here. I hope I've shown you that SPIN-POLARIZED is a useful tool to study magnetic order and coexistent with competing phases in quantum materials. It's tricky measurements because you need to bring your magnetic tip to the sample you want to study, which is not always easy. But still, I hope I've been able to show you that we can use it to image magnetic order in iron telluride and actually also manipulate the magnetic order in iron telluride. And in the second half, I've shown you that we can study coexistence with superconductivity in the iron chalcogenides. And well, if you think about what are interesting opportunities in using spin-POLARIZED STM to study these materials, I mentioned initially already, it would be really great actually to image what the magnetic order in these kind of, or whether there is magnetic order in these kind of structures, basically using a spin-POLARIZED tip. But I think the other application of spin-POLARIZED STM, which is becoming increasingly important, is studying these two-dimensional ferromagnetic materials, where basically, if you like, neutron scattering, you can't really use, because if you only have a single layer, that's not enough material. And with optical methods, you can say whether overall the material is magnetic, but you can't actually image the magnetic order. Whereas with spin-POLARIZED STM, in principle, you can image the magnetic structure in these structures. And I think if that's possible, then one can also explore ways to manipulate the magnetic order, as has been shown for nanostructures, for example, in this work from the group of Professor Wiesendanger, where they have created skyrmions in a thin film magnetic layer. And basically now one could try to apply this also to these kind of materials to try to write information into the material. And finally, I think one aspect which we've tried to figure out, but I think it's still work in progress. I think there's an important question of whether we actually see also inelastic excitations of magnons in these materials. So in the Peptide superconductors, I think there is evidence that one sees signatures of the spin resonance in inelastic tunneling. But the question is, in these materials where you don't have a sharp resonance, are these spectra actually strongly influenced, potentially strongly influenced by magnon excitations? And I think the fact that you get this V-shaped gap seems to be an indication that that's indeed true. However, if you like to nail it down by some smoking gun evidence, is not so easy. So one hope is that if one compares spectra taken with a magnetic tip, which is either parallel or anti-parallel to the sample, then maybe one can solve this puzzle. Okay, and with this I would like to end, and thank you for your attention.
10 seconds ahead of time. Chance.
What does the Fourier transform of the gap have to look like in the coexisting phase?
That doesn't show in the structure.
Ginsburg-Leddow theory, it must.
No, yeah, okay. It doesn't in our data. That's a good point, yeah, okay. we don't see any.
So when you use the spin-polarized tip, when you change magnetic field, so the tip, the direction of the moment of the tip will also change or not. Normally it's fixed. Because if it's not fixed, then the comparison with different field is become complicated.
So in the iron tellurium, we are fairly certain that only the tip fellows are not the sample.
The tip,
only the tip fellows. So we make deliberately a ferromagnetic tip, so that the tip follows, but the sample does not. But one has, obviously, from sample to sample, one has to check that.
If you just give ion atom message, that one doesn't change this field.
Yeah, that does change.
That's good.
Yeah. Well, if it's paramagnetic, you won't see any magnetic contrast without the field. And if you have a cluster, typically even for small fields, it will follow. But typically, in these studies, we've used fields where we are sure that it will follow. So a few Tesla. But for a properly ferromagnetic tip, much smaller fields are sufficient. If you want to study, for example, these 2D ferromagnets, one has to use lower fields because otherwise the sample just follows.
Yes?
Let me understand better. So you have shown that there is a charge density way together with
yeah.
But this is not nematicity.
Well, no, it's not nematicity, but you could wonder whether the two are linked.
And do you see that also?
Yes. Yes. That's charge contrast. Yeah.
So you see the charge contrast.
The V-shaped behavior there, this is in the magnetically ordered state?
Yes. So
why are you saying you don't expect magnets then?
I do expect them.
Okay.
Oh, no, sorry, I do expect them. The only difficulty is, I mean, I can say, oh, this looks like it's magnons, obviously, but proving that that's the origin, that's the
But magnons, I wouldn't expect a V-shape, right? I mean, as far as I understand it, I mean, there's this work from Scalapino and John Kirtley, right? And if you have paramagnons that are overdamped objects, then you would expect a V-shape in the paramagnetic state. But if you had magnons, they should be sharp objects or momentum average. Right?
Yeah, so exactly. That's why, yeah. So you have a continuum in the magnon density of states, and that's what we give you.
Okay,
so I think one can say it's consistent, but that obviously doesn't prove, right? So, and you can even argue that the fact that the curvature changes a bit, I mean, there's an anisotropy gap, so you can argue, again, you can argue it's consistent, but that's not a proof.
Yeah. Are there further questions? There should be.
Okay, I can add one point. Actually, we also mentioned this ion tellurium sample. We also see this kind of background. So it's indeed it's proof. I mean, it's the same. So it's a very strange gap. No, it's not gap. I mean, it's some kind of vision. Right.
If you were to do junctions, not STM tunneling, but planar junctions tunneling, do you also see the V-shape?
I'm not sure anyone has measured that. I don't know.
Una.
Maybe a naive question, but this magnetic tip experiment, can it be done on cuprates?
Yeah, in principle, yes. You just need to bring the tip successfully to the cuprate surface, retaining the magnetic tip. Yeah. But yeah, no, I think there's nothing to
it would be really interesting to see whether there is any magnetism associated with stripy patterns.
Yes, we tried once, but we should try again.
So later during this meeting, we will be told what happens in twisted bilayer graphene, where there's also some indication for magnetism of some sorts. Is this something that's completely crazy to study with, I mean, because the length scales being somewhat different?
I think it should be possible.
Yeah. Because there is some magnetism of some sort in some situations, so that Yes.
Yeah, simple question. When we're probing magnetic ordering with this technique, what is the time resolution that we have? Like how quick are the changes that we can observe?
So we don't have time resolution, basically. Well, it's not entirely true. As I mentioned, so the bandwidth of our amplifier is a kilohertz, and that's what's currently limiting our time resolution. So we see, for example, if we make these magnetic tips, right, you collect iron, and before it's actually stable magnetic, at some point you start to see that the tip magnetization fluctuates, and then actually we see that if you like, we see the magnetic order very noisy, and before it becomes really properly a stable magnetic cluster. But then there are people who do time resolved measurements in a kind of pump probe way, but that's not what we are doing. Yeah. And there you can get much better, much higher time resolution.
Further questions? Then we move on to the second. Let's first of all thank Peter one more time.